Okay, two more tests today, and these are pretty important ones. The integral test, and we'll do the P-series test in a second, which is actually pretty simple. Okay, so we have a continuous, positive, and decreasing for all x is greater than 1, right? So we have this function that matches these conditions, right? Then this is true. Okay, so we have a series. This is a series if you're not familiar, right? A series is a sum of all of your terms of a sequence, right? That's what this symbol means. That means add up everything. That Greek letter sigma means summation. Okay, so we are adding up a whole bunch of terms of your sequence. In fact, we're adding up an infinite amount of terms of your sequence. And we're seeing if that number goes off to infinity. If we add up everything like my bank account goes off to infinity, increasing and increasing forever, right? That's good to have. Or if it goes to 0, which is not good to have in your bank account, spending more and spending more and spending more money. Okay, so we're going to look at these things and compare it to its limits, right? Compare it to an integral. So this is how we do this. We're going to compare this series to the integral from 1 to infinity of 1 over 3x plus 4 dx. Right? Our integral needs to have variable x in here because we're integrating with respect to x, dy dx, rather than n, which our series has. Okay? So if this guy diverges or converges, that means this series will also diverge or converge, right? Which is why we're using this test. Maybe this is not a good integral, or maybe it's not a good sum, but it's a fairly easy integral. Okay, so this is called, hopefully you remember, an improper integral because it doesn't have an upper bound. It goes from 1 to infinity. When we have an improper integral, we change it and take the limit of a proper integral. Okay, this was what we did a couple of weeks ago when we had improper integrals as our topic. So now we're expected you to understand that the improper integral is solved by taking a limit and looking at the limit of your function. So the limit as b goes to infinity from 1 to b. Okay, and if you don't write this down on your paper for an FRQ, it is not correct. You have not done the calculus right. Okay, so let's look at this. Let's evaluate our integral from 1 to b. So what type of an antiderivative are we looking at here? A natural log antiderivative. You need to recognize this one too. Whenever it's 1 over a linear equation, 1 over a linear, that's a natural log antiderivative. 3x plus 4. Natural log antiderivative. And we have the absolute value when we take the natural log antiderivative. Now, one thing is missing. That would be because we have a coefficient of 3. That means we have a multiplying factor of 1/3. Because if we were to take the derivative of this, it'd be 1 over 3x plus 4 times 3, since that's the derivative of 3x. Okay, so we always have a chain rule derivative with a natural log function. So this 1/3 is here to cancel out your multiplying by 3 because we don't have that over here as a leading coefficient to begin with. Okay, and we're evaluating this from 1 to b. Okay, so let's come in here. Let's do our fundamental theorem. We're going to plug b into here, and then we're going to plug 1 into here. Equals the limit. We still haven't done the limit yet, so we still have to write it down. We are looking for the limit. 1/3 natural log of 3b plus 4 minus 1/3 natural log of 3 plus 4. Right? That's our fundamental theorem. We evaluate it by plugging the top value in minus evaluating when you plug the bottom value in. So now let's actually look at the limit of each of these parts. What is the limit as b goes to infinity of a natural log function? Okay, thinking about the graph of a natural log, it grows logarithmically, but does it have an upper bound? No. So this one is infinity. The limit of a natural log function as b goes to infinity is infinity. And what about the limit of a constant, right? This is a constant. The natural log of 7, that's a number. Divided by 3, that's another number. So what's the limit of a number? 0, because it doesn't have a slope, right? It's a horizontal line. It does not have itself a slope. Okay, so let's go back over here, right? We did all that work so that we can now compare it to our series. So, does your series converge or diverge? Well, what happened to your integral? Did it converge to a number or diverge to infinity? This one diverged because it had a limit of infinity, which means this one also diverges by the integral test. That's exactly what I did, is I performed an integral test, and I found that the integral diverged, therefore the series diverges also.
Just divide my answer by 2.
Okay, let's check out 1 over n cubed. 1 over n cubed, we're going to compare this to the limits from 1 to infinity, the integral from 1 to infinity of 1 over x cubed dx. Okay, so this improper integral, we take the limits as some value approaches infinity of 1 to that value. Right? It can be any letter you want, except for x, of course. So 1 over b, 1 to b of 1 over x cubed dx. Okay, now maybe it might help us to rewrite 1 over x cubed in its polynomial form, which is x to the minus 3 power. Right? Maybe that will, because this is not a natural log antiderivative. X cubed is not linear, so we change it into a polynomial so we can apply the power rule. So what's the antiderivative of x to the negative third? Well, that would be x to the negative second, because we add 1 to the power. Negative 3 plus 1 is negative 2, and then we divide by negative 2. So if I rewrite this as a single proper fraction, that's the negative of 1 over x squared from 1 to b. So if we continue, we're still looking at the limit as b goes to infinity of our fundamental theorem, which says we plug in b and then minus what happens when you plug in 1, right? It's a subtraction. So this is negative 1 over 2b squared minus negative 1 over 1 squared, which 2 times 1 squared is just 2, and minus a minus is a plus. So now let's actually look at the limits. What is the limit of 1 over 2b squared as b goes to infinity? Right, that's 1 over infinity, which is 0, right? Really, 1 over a really large number. Plus 1/2, 0 plus a half is? Well, that's 1/2, right? A constant. It comes to, it actually converges to a number. It converges because the limit of this happens to be 1/2. Okay, so our integral converges, so what can we say about our series? It also converges by the Integral test, because that's exactly what we did. Integral test. Okay, so here's another thing about the integral test. If the series converges, then that series will always be between the integral and then the first term plus the integral, right? So we can have an upper bound and a lower bound of convergence. We might not be able to figure out exactly what it converges to, but we can get it in a ballpark, right? Between -6 and -5. It'll converge in between those two numbers. Or between 0 and 1/2. Okay, it can converge between those two numbers. So let's do that for this one. Okay, what was our, right, we just did this up above. What is the convergence? What does anyway, what does this function converge to? Right, we just did this. This converges to 1/2. And that's supposed to be an x. So that's the lower bound is less than the sum of 1 over n cubed, right, from 1 to infinity. And what's the upper bound? Well, in order to figure that out, we have to know what the first term is. So what's the first term of 1 over 1 cubed? That's 1. So what's 1 plus 1/2? 1.5. Okay, so we know that this sequence will converge to something between 1/2 and 3/2. Right, and that's a pretty big range. There are lots of numbers between 1/2 and 3/2, but at least we can put an upper bound to it and a lower bound to it, so we have a better idea of what this is going to converge to. Right, and of course, in case this is some random, super awesome thing that we don't know the numbers for, we would use the integral test to find these bounds of convergence, the upper bound and the lower bound. Okay, let's transition to our next test, which are p-series, a p-series test for convergence. Okay, so like it says, if we have 1 over n to the p, right, so now p is going to be your power of your function, right? P stands for power. 1 over 1 to the p, 1 over 2 to the p, right? Where n is always 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 over n to the p is called a p-series, where p is a positive power. Okay? P stands for power, I guess. So if p equals 1, then we have this harmonic series. Okay, harmonic, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, right? Harmonic. There's harmonic sequences and geometric sequences and arithmetic sequences. Okay, so some special things about harmonics. So looking at these, which ones are going to converge, do you think? And which ones are going to diverge? So we have all these ones. So let's write them as powers. So this is n to the first power. So this would have a p of 1. This would have a p of 2. This would have a p of 3. What about the square root? That's the 1/2. Right? So we can rewrite this one as the sum of 1 over n to the 1/2. Right? It has to be a power. In order to use the p-series as a test, you have to have a power, right? Or we're not using p, we're using something else. What about this one? What is the power of that denominator? P to the 3/2, right? Or, sorry, not 3.5, my brain. 3 divided by 2, or 1.5. Right, because this is n to the first times n to the 1/2. And when we have the same bases, we add exponents.
So then would it be n to the power of 3/2? Or would it be p?
Oh yes, of course the letter doesn't change, mi siento. N to the 3/2. N, yes, 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 yes. N, these are all N's. N, A sub N. Because N starts at 1 and goes to infinity. Okay, so here are the rules. If we have a P series and our P value is greater than 1, then our function is going to converge. Okay, we saw an example a second ago where we had a P of 3, right? 1 over n cubed. 1 over n cubed converged. It has a power of 3. Okay, what about if we had a fractional power between 0 and 1? What do you think? This is going to diverge. Diverge. Because as you take the square roots, they get to be, well, 1/overs, and we add them all up, and we get something that doesn't go to a single number. And then if p equals 1, so 1 over n, converge or diverge, what you think? It actually does that. Adding up a whole bunch of fractions, starting at 1, 1 plus a half plus a third plus a quarter plus a fifth plus a sixth plus a seventh, right? Does not add to go towards a single value. Okay, so it diverges. So looking up here, which one of these ones converge? 1 over n squared. Yes? What else? Cubed, n cubed, right? It has a 3 as its power. What else?
1 over n times the square root.
Right? The n to the 4th, obviously. 4 is bigger than 1. And then we said this one was the 1.5. So all of those are summations or series that converge to a single number. Right? And we can say they converge by the p test, and we just have to tell them what the power of your function is. And then these guys are going to diverge because we have a p-value greater than or equal to 1. So when we're looking at these, we just have to basically identify the power. So part A, would this one converge or would it diverge? This one would diverge. So we write with words, diverges by the P series test. With P equal to what? 1/3, which is less than 1. Okay, part B, what would you say about this function? Converges or diverges? This one is going to converge by the P series test with a p-value of 5/4. And how does that compare to 1? Greater than 1. And that's what you have to say if you're going to use the P series for convergence or divergence. Okay, pretty good stuff. Have a swell day.